Hi, today we're going to talk about the binomial distribution or the binomial probability distribution function. The binomial distribution function is a function that has two outcomes. And it's not, you'll often see it as a flipped coin, right? You flip a coin and it's either going to be heads or it's going to be tails. Uh, and a lot of people immediately, when they think about the binomial probability distribution, immediately think that it's a 50-50. There's a 50% chance that it'll be tails and a 50% chance that it'll be heads. Well, part of that reason is because we always use or often use the flipped coin example to try to teach the binomial distribution. We're going to walk away from that because I don't want you to consider that it's only going to be a 50-50 because it isn't. And so in class, when you're in a physical class, the professor sits up at the front and he's lecturing and he's waiting for somebody to walk in the door, and there's always a student that walks in late, and the student, he puts his head around the corner and he's like, oh, should I walk in or should I not walk in? And we're going to pretend that this student peeks his head around the corner and he either is going to wear a hat or he's not going to wear a hat. And in the old days, wearing a hat indoors was kind of a rude thing, and students kind of do it now. So the question to us today is going to be hat or no hat. No hat. Okay. So we're going to find out what is the probability that somebody's going to walk into your class with a hat or a no hat. Well, most of the time, let's say in a regular class of 40 students, we have 5 students who wear hats on a regular basis, 5 out of 40, and that means that 35 out of 40 students do not wear hats on a regular basis. That actually can reduce down, right? So that's going to be, 1 out of 8, and this is going to be 7 out of 8. So that'll be a little easier for us to handle. So let's find out what it is that constitutes a binomial distribution and whether our guys are going to have hats or no hats. So what makes this a binomial distribution to begin with? What makes this a binomial is that there are only 2 choices, 2 outcomes. Okay? It's not that it's a 50-50 chance, it's that there are 2 outcomes per trial. We have to find out that all trials are the same, meaning that there's just an equivalent amount of chance that the next person that comes in is going to have the same probabilities are the same. And we have to figure out that one of these is going to be equal. We're going to assign this one to P, meaning that's the probability that someone's going to walk in with a hat. And that means that the other one has to equal to 1 minus P. If you notice, if I take P plus 1 minus P, it's going to equal to 1, right? This guy and this guy cancel each other out. So what we're really saying is that the probability of somebody walking in with a hat has to be plus the probability of somebody walking in without a hat has to equal to 100%. Finally, we're going to count n, or the letter n, as the number of trials. So if up to 3 students walk into the class, and that's 3 different trials, but we're calculating the probability based on everybody else. So what we're really interested here when we finally do our math is P, which is the probability of, in this case, hats, 1 minus P, which is the probability of no hats, and N, I'm going to pick a number, 5 students who could potentially walk into the class late. Okay? And again, let me just draw a little door here just for, so here's your guy, and he's late for class. And that's a little visual effect there because it's fun for no other reason. To this end, we are going to have to use a combination, NCX. And we'll do combinations in a separate video, or you can go out and find that one. But I'm going to assume for the purposes of this one that you know how to calculate a combination. And we'll go through one here in a minute. And we're going to take that combination and we're going to multiply it by the probability that something is going to happen times 1 minus the probability of n minus x. Now this doesn't need to be very complicated. Let's work through it together. Again, P is the probability that something's going to happen, right? In our particular scenario, P is going to be 1/8. Let's turn that into a decimal. Actually, we don't have to. That's going to be 0.125. 1 minus P is equal to 7/8 in our scenario. It's the probability that the person who's going to walk in is not wearing a hat, and that's going to be 0.875, right? N is the total number of possible outcomes, right? Total number. And in this case, we said we had 40 students. So let's just say 40 students are going to walk in through the door. And I'm going to try to ask the question X. How many successes? And so I've said 5. What does that mean? I want to know what is the probability that 5 students will come to class with a hat. That's the question. So this is the total number that we want. This is the total number of students altogether, and these are the probabilities of walking with a hat or not walking with a hat. Again, we're going to do n combination x, p to the x, 1 minus p to the n minus x. And let's break this into 3 separate pieces. Okay, first we have the combination. This is the counting portion of our combination, our probability. Okay, this is going to tell us all the different ways that this could or could not occur. So that's section 1. Number 2, we have our success or our winners. Okay, in this case, this is going to give me the probability of hats. Students that walk in with a hat. How do I get that? Well, here's the probability of any one person walking in with a hat, and here is the probability of, or not the probability, but the total number of successes, right? In this case, this guy's going to be 0.125, and this is going to be how many? Well, 5. How many? 5. If that's the case, if this is 5 students, and I have 40 total, 40 n minus 5 is equal to 35. That makes this guy all the students that have no hats. Remember, in a binomial distribution, it is 2 outcomes only. 2 outcomes only. So you have to be with a hat or without a hat. You have to be here or here. And that means that these guys are with a hat and these guys are without the hat. And that makes sense because this is the probability of walking in with a hat, and this is the probability of walking in without a hat, right? Now let's go ahead and do the math in our little fake example. N, I don't like that color, let's do one of these. N combination x, p to the x, 1 minus p to the n minus x. All right, so this is n. There are 40 total students. We're going to do a combination with 5 successful outcomes. The probability of walking in with a hat is 0.125 to the x to the 5 times 1 minus 1.25 to the n minus x, to the n, 40 minus x. Those are the, I did it again. 40 minus 5. Those are students that are not going to walk in. And let's work this in a couple of different portions here. 40 combination 5 is going to be 40 factorial over 5 factorial 40 minus 5 factorial. Again, if you don't know where that came from, you've got to figure out how to do combinations somewhere else, and that's okay. 1.25, I might as well do that one now. Let me bring out my calculator. Clear. 0.125. Do I have an x to the, I don't have an x to the y here. Let me change this to a different scientific. There we go. 0.125, and I'm going to make that x to the y 5 equals, so this is going to be 0.00, where'd it go? 1, 2, 3, 4, and then the 3. 0.00003 times 1 minus, that's a 0. Wait, I get that wrong. This is going to be 1 minus 0.875. My apologies for that earlier. So that's going to be, no, I had it right. Because now we're going to do 0.125. Then this guy becomes 0.875 to the 40 minus 5. Let's go ahead and do it just like we did the other one. Get this, scoot it over so we can see it. Clear. 0.875 x to the y, 40 minus 5 is going to be 35. 5 equals 0.009. 0.009. Okay. Let's rewrite this again. So that's going to be 40 times 39 times 38 times 37 times 36 times 35. Note, I'm going all the way to 35 for a reason. Over 5 times 4 times 3 times 2 times 1 times 40 minus 5 is 35 factorial. So 35 times 34 and so on times 34 up here. These guys are all going to cancel out with these guys, and so we can do that one again in a second. 0.00003 times 0.009. We can go ahead and multiply those together. Right? 0.00003 times 0.009 equals 0.0000. Oh man, 1, 2, 3, 4, 5, 6, 2, 7. 0.0000027. Wow. Okay. So now we got to go back and figure out this whole mess. All of this has been canceled, so this is the only one that I'm really going to worry about. In this case, let's see. I can cancel the 5 and the 40. That turns into an 8. I can do the 4 and the 8. That turns into a 4. The 2 and the 4. That turns into a 2. And 3 and the 36. That turns into a 9. So let's rewrite this. So let's rewrite this. 2 times 39 times 38 times 37 times 9 times 0.0000027. All right. That seems a little complicated, but just play with it until you get it right. Or practice it. Don't play with it. Practice it until you get it right. Let's do that. 2 times 39 times 38 times 37 times 9 times 0.0000027 equals 0.266. So 0.266 or 26.6%. So what is the probability that 5 students will walk into my class with a hat? 26% chance. Again, what's important about the binomial, or what we find out then, is that we're going to run, the probability that x, then we're going to do this for each one of these. Probability that x equals 0, the probability that x is equal to 1, the probability that x is equal to 2, and so on. Luckily, in the back of your book, equals to 3, probability that x is equal to 4. Why do I keep doing this? If you go to the back of the book, you'll find that these calculations are already done for you. So you should do 2 things. Number 1, you should be prepared to calculate any one of these or maybe more importantly, be prepared to pull the number from the back of the book. And the reason I keep writing this is because at some point we're going to actually graph these out. Remember, this is a discrete probability function. 0, 1, 2, 3, 5, 6, 7, 8. And most of these curves in the binomial distribution look kind of like this. They go up, they start high, and then they come down and they tail off. Not quite a normal curve. You'll see because we start here above this normal and the number gets chopped off. But it goes fat, and then it has a long tail. That's a very traditional binomial distribution. That's what they look like. And so if you were to look at the probabilities in the back of the book, in our case, we said 5, and this guy was, so the probability of this guy was 26% in our example. But if you go to the back of the book, you can calculate those out. Remember that the binomial distribution is not quite a normal distribution. It starts fat, and then it gets skinny over here in the tail. Remember that a binomial distribution has two outcomes. Sometimes they're 50-50, but that doesn't necessarily mean that the probabilities will be 50-50. Okay? All right, good luck.